Hello, greetings. Today, definite integration from first principles. We're going to attempt to actually find from first principles the integral of x squared dx from 3 to 6. There's a lot of YouTube videos that have this particular integral, normally from 0 to 1. We're going to do it from 3 to 6 for variety, so a little bit different, I suppose, with all of this. And I must say, I'm not prepared at all for this particular video. I haven't done this type of work for many years, so if I mess up, you're free to laugh, I suppose. This is also known as integrated by with Riemann sums. So it's a Riemann integration. Let's write it here. Riemann. I hope I'm spelling it correctly as well. Riemann integration. So we're going to be looking at Riemann sums. And this is really from what definite integration is from first principles. First of all, let's evaluate this so we have an answer for what we ought to be getting eventually. So that's a very easy integral, of course. It's a third x cubed between the limits of 3 and 6. So 6 cubed is 216 divided by 372. So that's a 72. Take away 27, take away 9 is 63. So this should give us 63 here. But of course, we're going to do it very differently now. And before we set our work up, we're going to look at the general setup so we are kind of like understand what I'm going to do with this particular one later on. So this is now, let's say, some kind of curve, f of x, and this is the x-axis. And of course, the definite integral, we can interpret this as the area under the curve. So let's say we have to find the area from A to B here. And this is this kind of section here. We're going to split it into equally spaced strips from A to B. How many of them? N, let's say. And I'm going to put a few on this particular side. So each strip has a thickness delta x as per usual notation. So the thickness here is delta x. And what is delta x? I'm going to write it up here. Delta x, quite clearly, if the strip is from A to B and is n of them spaced out, it's going to be, of course, b minus a divided by n, so equally spaced. Okay, so now the question is, if we take an arbitrary strip, let's say this one here, I've just drew and I'm shading it. Of course, what is the area of this particular strip? Well, quite clearly, it's going to be delta x. And what is the height of this strip? Oh, first of all, what kind of shape is it? This is a rectangle. Clearly not. It's some kind of maybe a trapezium with a curved end on the top. So how are we going to define how tall it is? We're going to approximate it to a rectangle, quite clearly. That's the best we can do. And where we're going to draw the height? Are we going to draw it to the right, to the left, somewhere in the middle, quarter of the way, perhaps here? The answer is, as it turns out to be, it hardly matters. Eventually, what we're going to do, we're going to let the number of rectangles go to infinity. How we're going to do that is by just making them finer and finer and finer. So they're going to be so minute, so it hardly matters whether we measure the height here, or anywhere. So you can think of it as I want to take an average height. Okay, so the average height, so how can I mark it here? I'm going to mark it on the right, but that need not be on the right hand side. It's going to be the height of f of x. Well, not quite, because of course, how do I define that this is my f of x here, this height of this particular rectangle? Which rectangle is that, is the next question. Well, it's the ith rectangle, where that's the first, the second, the third, the fourth, the fifth, and so on. And of course, this is the nth one. So the I, if you want, runs from 1 to n. So of course, we want to the height of this particular rectangle is f of xi. And now what is xi? This is where the xi is. Let's say we mark it on the right. I have no space to put the delta x and the xi on the same picture. Xi, if you think what it is really, is from the a. This is this position here is going to be A, the start of my interval, plus 1, 2, 3, 4, 5, let's say, so plus I lots of delta x, wherever we choose to draw it. So if it's on in the fifth rectangle, it's going to be, of course, wherever we're starting, plus 5 lots of delta x. If it's the seventh rectangle, it's going to be wherever we're starting, plus 7 lots of delta x. And this is, of course, now what I didn't write anything at the front. This is my x I. And with delta x, of course, I have defined it up there. And the f of x, we need to know the equation of the curve, and therefore we cannot really write anything for it. So what is this area? Well, this area, let's actually write it here. It will not actually fit if I start from there, because I've got a very long expression to write. I'm going to say that my area, I'm going to call it capital A, is the limit. Let me move out of the way so we can see the picture and what I'm writing. Is the limit as n tends to infinity. So if I make this rectangles finer and finer and let the number go infinitely large, it's the sum of all of these rectangles. So it's the sum from I is equal to from I is equal to 1 to n. And I'm going to let, of course, n go to infinity eventually. So at the moment, it's going to be, of course, width times length. So the width is going to be f of xi. Not the width, sorry, the height. I beg your pardon. I'm saying a lot of stupid things. I said I have not prepared for this. I haven't done this for maybe well over 10 years. So each rectangle measures delta x by f of xi. We're going to add them all up. So we add them all up, and then we're going to let the number of these rectangles go to infinity. This definitely should give us the area under this curve. And of course, I have defined each and every quantity that I've got in there. There's my delta x, there's my xi, the f, of course, f of xi, I can't really put in there. In this case, it will be, of course, this quantity squared, but here I don't have the equation of the curve, and therefore I cannot do it. So let's try now to apply this to our particular curve, which is, of course, the integral from 3 to 6 of x squared dx. And let's see what we're getting. We know with our normal formulas and established things that we can do that in a few seconds. Is actually 63. Will we get 63 is the question. So this is now how we're going to find the area from first principles. Area is equal to, so I'll put the limit from the beginning. Let's put it from the beginning. Limit as n tends to infinity of the sum of all the rectangles starting from I is equal to 1 to n. And of course, we're going to have, I'm just merely copying that, which is f of xi times delta x. So this is our quantity, this is our limit, and this we hope that eventually is going to give us the 63. Okay, let's start putting things in. Limit as n tends to infinity, the sigma, and let's establish some of these quantities according to how we define them. First of all, the integral that we got is from 3 to 6, which means basically our a is 3, our b is 6, and therefore our delta x is going to be 6 take away 3, which is 3 divided by n. So this is the delta x. I'm going to write it first because that's actually easier. 3 over n. And let's put a little indicator what this bit is. This is our delta x. So the question now is, what is our xi? Not the f of xi, just the xi to start with. So let's think about what this is. So xi is going to be a, we're starting at 3, and we have I lots of delta x, and delta x is of course 3 over n times 3 over n. So in the simplest form, it will be 3 plus 3i over n. So this is our xi. Let me just move out of the way so we can see it. So we want f of xi, And the function f is, of course, x squared. So this is all of this squared times 3 plus 3i over n all squared. And this is inside the limit, and all of this is inside the sigma. And this quantity here is our f of xi in this particular case. So now we have to be patient and evaluate this sum and then take eventually the limit. I don't think I need any of these things because I might need a bit of space now with this kind of work. So let's clear the board and let's think about all of this and how we're going to approach it. What kind of maths is it needed here? Well, we need to know, first of all, how to sum standard series. They're like the sum of integers, the sum of squares and things like that, which do come in further maths, I think, these days. And we need to know some basic limits, some kind of like fairly obvious limits. A lot of this these days are taught at university, but I think a lot of this now also have started appearing back as they used to be in further maths. So let's do this now step at a time. Okay, limit. The limit's, of course, the last thing that I'm going to do, and that's why I consider, shall I just leave it and just work this out, and once I have it in the simplest form, just put it in at the very end. Okay, first of all, the limit has a, well, I don't know if I can call it dummy variable. It's in n, so nothing that has n can go outside the limit operator. And the sigma, the dummy variable, is I, and therefore anything that has I cannot go outside the sigma. So if we look at this 3 over n, it can go outside the sigma operator. So let's put it outside first of all. That's the 3 over n, and that will leave us inside sigma I is equal to 1 to n. And this bit here, rather than squaring it, I'm going to factor out a 3, which of course is going to be squared, so it's going to be a 9. I'm going to do several tidies along the way. So it's going to be 9, and then I go 1 plus I over n all squared. So this is inside my sigma at the moment. So I've just squared that, close the bracket for the limit. Okay, can I fit one more line in there? And what else can I do? I'm going to do 2 steps at one. I'm going to factorize a 3 times 9, which is 27, which is just a multiplicative constant. It can go the 9 outside the sigma, and now a 27 can go outside the limit. So it makes the interior a little bit better. So 27 times the limit as n tends to infinity. I still got the 1 over n inside my limit from this quantity here, and inside the sigma operator now I have from I is equal to 1 to n just simply 1 plus I over n all squared, close sigma and close limit. Okay, need some space quite clearly, so let's go to the top and let's start rubbing things off. So the area is equal, let's take the top 3 lines, and hopefully haven't made any mistakes so far. All right, equal 27, limit as n tends to infinity, my 1 over n. And now I need to square, this should be n there, it will go wiped out. Okay, I need to square this quantity inside my sigma operator. So this is equal to 1 plus 2i over n, 2i over n plus I squared over n squared. That's the argument of the sigma, close limit, equal 27, limit as n tends to infinity, 1 over n. Linearity now of the sigma operator, I'm going to split into 3 separate sigmas. I forgot to put my particulars on the sigma. That's from I is equal to 1 to n from this line here. So I'm going to have 1 over n sigma I is equal to 1 to n of 1 plus, on the next sigma I've got this quantity here, the n, remember the sigma is running, the dummy variable is I, so the n is a constant. Although it appears up here, that's not a problem, it's actually a constant as far as the sigma operator is concerned. So the 2 over n times the 1 over n, so 2 over n squared, the 2 from there, the n squared, I can pull it outside the sigma. That's the second sigma, that is. And then I'm having from I is equal to 1. And what I've got left in there is, of course, just I. Okay, just this I here. And I've got one more sigma. The 1 over n squared, as far as the sigma again, is a constant. But I've got another 1 over n at the front. So it's going to be 1 over n cubed. And then inside the sigma operator, I will be left just with the I squared. And let's hope, oh, it's all sound so far and I haven't missed anything. Okay, let's make more space and let's start now evaluating some of this stuff. Okay, 27. The limit as n tends to infinity, and summing loads of ones from I to n is just n. This is the sigma. N over n is just simply 1 plus 2 over n squared. Now the sum of integers from 1 to n, standard result from further maths, is this one here, a half. You normally have it in n. We're going to have it in i's now, of course. It says, sorry, not in i's. You normally have it in r's there, the dummy variable. When we have it in i's here, the answer is, of course, a half n plus 1. So that's going to be times a half n plus 1 plus 1 over n cubed. And as that's the sum of squares, so this is going to be, is it 1/6 or 1/3? I think it's 1/6. 1/6 n 2n plus 1, n plus 1. I'm totally unprepared for this. I hope I'm not writing stupid things down. Times 1/6 and I don't even know why I wrote it in that order as well. n plus 1, 2n plus 1. Okay, so now we need this limit. Loads of tidies to take place still. Let's make some room again and let's do our thinking with limits now. So this is going to be 27, limit n to infinity. So that's exactly the same. So I'll take this line off and hopefully we're going to get that 63. Doesn't look like a 63. 27 to become a 63. Better get to some kind of fraction here, otherwise this is not going to happen. 1. This is this one here. 2 times a half cancel. So I'm going to have on the next one as n plus 1 over n squared. And this one here, I'm going to have on the numerator plus n plus 1, 2n plus 1 over 6n cubed, close our bracket. And those who are very good with limits can actually see very, very quickly what this will produce. I'm going to do a little bit of work with this. I'm going to show you a few more steps perhaps. Okay, not necessarily by writing loads of lines here. What we can do, first of all, we can cancel an n here. So this will become just simply n, and this n on the numerator will go. We can also lose the n from this numerator here, and this will become n squared. Makes it a little bit easier. And then I can actually split this particular quantity, still inside the limit. I'll add it afterwards. 1 plus n divided by n is 1 plus 1 over n. So this is just this fraction split. And if I expand this numerator that I've got in there, I'm going to get, let's write it here, 2n squared plus 2n plus n plus 3n plus 1 over 6n squared. So if I split this fraction now, again in exactly the same way, 2n squared over 6n squared is going to be, first of all, 1/3. 3n over 6n is going to be 1 over 2n, and lastly plus 1 over 6n squared. I hope I haven't made any mistakes there. And we are almost at the end, and let's hope we're going to get the right answer. Our area is given by this limit as n tends to infinity. As n tends to infinity, clearly 1 over n goes to 0, 1 over 2n goes to 0, 1 over 6n squared goes to 0. I forgot the 27 there. So what's our answer? Our answer is 27 times 2 1/3. 2 1/3 is 7/3. So that's 27 times 7/3, and I think we're done. Because of course, this is 63. We managed to actually get this integral in a fairly analytical way, and in a way that perhaps we ought to appreciate how easy we have it. Imagine if every integral we had to do, we had to go through a limiting process exactly like we went through. I mean, we're very, very lucky. But this is how it goes, and I hope you followed it. Because I didn't actually look at this proof before this lecture at all. I haven't done it for a long time. Maybe I didn't explain it as good as perhaps I could have explained. Perhaps I was to do exactly the same lecture again. I will be a lot better. But I hope you understood what is going on with Riemann sums. That's what this is basically, and integration. I hope you enjoyed it. Who's laughing now? I will see you very, very soon.